Hi everyone, I'm Sangin Lee and a volunteer introducing Dr. Higgins to audience and deliver questions to Dr. Higgins. I'm very honored to introduce her today. Dr. Raegan Higgins graduated summa cum laude with BS in mathematics from Xavier University of Louisiana in May 2002, and she started to study at University of Nebraska-Lincoln in August of the same year. She wrote oscillation theory of dynamic equations on the timescales in a doctoral dissertation under advice by Dr. Lynn Erbe and Ellen Patterson in May 2008 and was one of the first two African American women to earn a doctorate in mathematics from the University of Nebraska-Lincoln. She has been an associate professor of mathematics at Texas Tech University since 2008. Today she is going to give us a talk about modeling in and broadening mathematics.
Good morning, everyone. Thank you to the organizers for inviting me to speak at Math for All. New Orleans is my home. Oh, I should say my second home. I'm sad because of COVID because I would love to be there this season. As you would say, it's festival time. I was so excited to be able to have some crawfish, but clearly this is not working because I'm sitting here in Lubbock, Texas, not um, in New Orleans, Louisiana. Thank you for the great introduction. So today I'm going to talk about modeling in and broadening mathematics. This is, think about this as a journey talk. I want to be able to reach everyone. The title is Math for All. So I want to um, show my journey at all the stages of in mathematics thus far, and hopefully someone can see their entry point into mathematics. So let's get this technology going. So first, let's start with my journey. Born in Baton Rouge, Louisiana, academic dialogue was something that was very heavy in our evening conversations all the time. The phrase was, did you do your best? So we weren't so, at least at an early age, I don't remember my parents being very grade focused. It was more, did you do your best? If you did your best, that's all I ask. Women in STEM were very prominent in my life. I didn't know that it was STEM at the time, but that's what it was. My mom minored in computer science, I was majored in computer science. I have twin aunts. One's a computer scientist, another is an engineer, and my aunt is a nurse as well. So I knew lots of women that did mathematics and engineering, and it was just, really commonplace. I was an okay math student. The start of my birth to mathematician was in eighth grade. I did not take pre-algebra, so I went from regular seventh grade math to ninth grade math, and I didn't have pre-algebra, and I was doing poorly. As you see on the screen, these are some of my exams. So you can see lots of F's, right? I still have these exams in my office. I know where they are. I use them some days as reminders of the things that you can accomplish. And you see one of them, I said, doesn't count, we'll take a retake. So my teacher in algebra was Mrs. Gwendolyn Scott. She did not play. There was no, I cannot. Her motto was simply like my mom's and my parents, but it wasn't said that way, but it was, did you do your best? And she was like, you can do better than this. And for a while, I got along with being able to say, oh, I didn't take pre-algebra. And she was like, okay. Then eventually she was like, this is not working. You're going to take these exams home and you're going to get them signed. Oh, wait, what? Signed? So I got to tell them about my grades? This is not a good thing. And my parents had this philosophy: for every C you made, I was punished 6 weeks. So basically the period of until you got the next grade. Make it F's, I'm going to be punished the entire eighth grade. I got to do better than this. So I found my self-confidence in mathematics. So you'll see there's some A's, but even, I was happy with my C's, honestly. I was like, I made a C, this is great. But I got some A's and I found my self-confidence. And it was like, okay, I can do mathematics. From that day, the end of eighth grade, I wanted to be Mrs. Gwendolyn Scott. My goal was to teach algebra, maybe, and because I hadn't seen any more math since then, I was going to teach algebra and I was going to inspire students, and this is what I was going to do. This is my life plan. So I went to Xavier University of New Orleans, Louisiana. My family has great history there. So it was I'm not going to say expected, but it definitely was on the radar. So I chose to go to Xavier. While I was there, I minored in computer science. I did a lot of community service. I was one of the inaugural members of the Gates Millennium Scholarship. I did undergraduate research. So I was doing all the quote right things to set myself on a path to go to graduate school. I wasn't necessarily thinking about graduate school, but my advisor, Dr. Vliko Kosick, who was chair of the math department at the time, my Cal 1 and Cal 3 instructor, started doing research with me during the Model Institute for Excellence. So this was our first research problem. Describe the dynamics of this difference equation. I started working with him as a second semester freshman. I had only taken Calculus 1. What are dynamics? What is a difference equation? What are you doing? He was like, oh, you have Cal 1. You can learn these things. So I had to learn this new vocabulary. Think about equations only on the integers. Okay, well, that's easy. I can easily do that. No big deal. That's how children count. I can handle that. But things like stability, attractivity, bifurcation, what do you mean? How am I going to learn how to do this? So over the duration of my time as a student at Xavier and doing undergraduate research, I came up with these diagrams. So we did a lot of work. He taught me a lot of things. We worked at slow paces. I did presentations, and I was, amazed that with my understanding as a first semester freshman, how I could grow in mathematics and be able to do these things. So it was exciting. I was like, okay, I can do these things. So it led to some great work, and again, increasing my self-confidence. As a result of working with Dr. Kosick, he sent me, and I say sent on purpose, he sent me to the Nebraska Conference of Undergraduate Women in Mathematics. It's like, you're going to go to this conference and you're going to present this work. I'm going to do what? Now, a part of being at Xavier, we would present it, but you present it to your peers. So you weren't really worried about this critique or, it's like, oh, these are my peers. They know me. I can do it. He was like, no, you're going to go. So I went to Nebraska Conference of Undergraduate Women in 2001 as a junior, and I presented on this thing, on our work. But what it led to was my advisors. So Dr. Irby's at the back with the glasses on his shirt, and Dr. Peterson with the red shirt on. They came to my talk and they said, do you want to come to an REU? And I was like, what, in Nebraska? No, they had never been to Nebraska before. Where's Nebraska on the map? It was February when I went. I froze to death because I did not have the appropriate coat. My Louisiana coat is more like a jacket in Nebraska. I froze to death. And they're like, you know something besides calculus. You've worked on integers, so we're going to teach you this new area of mathematics. Do you want to come do the REU? Well, I mean, yeah, if my advisor found out that I said no, I would be dead. So I went to UNL. I went to the summer program EPSCoR there the summer of 2001. So this was our research problem. Use these so-called Taylor monomials. You can read it on a time scale. Well, what's the time scale? What am I supposed to do with this? How am I going to figure all this stuff out? This is me presenting with, we had a mini conference, so you had to make a poster. Now, this was a time before Beamer existed. So you would type your stuff in LaTeX and then turn it in PowerPoint, turn it into an image, and then take the images and import them into Beamer. That was the most tedious process. So if you found a mistake, you had to do the same thing over. But this is me presenting. There you see I'm using my hands. It's something that I still do. And then I had to learn this new vocabulary. Time scales, there was lots to learn. You had an REU for 8 weeks. How am I going to learn this? And he was like, just take your time, learn what you learn. So that was my introduction to the field of time scales. What that led to was me eventually going to the University of Nebraska-Lincoln to pursue my PhD. So I applied to other schools. My top choices were Emory, the University of Maryland, College Park, and UNL. And with the Packard Foundation Fellowship, I chose to go to UNL. So I became a Cornhusker. So I'm off to graduate school. As was mentioned in my introduction, Christina Eubanks and I received our PhDs from UNL in 2008. It was, I guess for us, we didn't know the history that we were making because the goal was to get done. We came in together, we wanted to start together. And then once it all happened, they were like, do you know that you did this and you did that? And we were like, oh, no. The goal was to start together, finish together. So looking back on it, yes, we made history, but at the time it was, I came with my friend, Christina and I went to Nebraska. We went to Xavier together. So we agreed to go to graduate school together. So it was one of these things, you start together, you finish together. So that's a little bit about me. So now you know something about my history, my background. As was said in my introduction, after I graduated from UNL, I went to Texas Tech. I was at Texas Tech as a visiting assistant professor for 2 years. Then I did tenure track starting 2010. And I'm associate professor. And my plan is to go up for full in the next 2 years. So cross your fingers, cross your toes. Let's do it. Okay. So what am I studying right now? This is one of my current research problems. So modeling in mathematics. So the research question is, can time scales be used to model prostate cancer treatment? So as you heard in my introduction, I studied oscillation theory. So I am a theoretical applied mathematician. That's the way I like to describe myself. So doing types of modeling problems was a big stretch for me. I wanted to always do these type of problems, but how do you get it done? Well, time scales was created in 1988, so it's a relatively new field. So the theory is still being developed and much modeling had not been done. But when you have students, students encourage you to, branch out in ways that you want to branch out, but don't quite know how. So can time scales be used to model prostate cancer treatment? So intermittent androgen deprivation therapy is a common treatment for prostate cancer. So as intermittent says, there are pauses. So IAD requires patients to alternate between periods of androgen suppression and no treatment. So that's why it's called intermittent. So this is more of a cyclic type of therapy. There are periods of on treatment, periods of off treatment, periods of on treatment, periods of off treatment. And during those times, a patient's PSA level, prostate specific antigen, is monitored. So that's the volume basically of the tumor. And they want to know how much cancer do you have. So you use the volume of the tumor to figure that out. And if it's above 4 microliters per gram, then you say this is a good indicator of cancer. So traditionally, continuous ordinary differential equations have been used. Everything is happening on R. Well, we know that's not really the case because there are periods of on treatment. So you're on treatment, then you're off treatment, you're on treatment, you're off treatment. Time scales allows you to deal with these pauses. It hadn't been done before. It just assumed we're doing it always, or we're not doing it always. And you do some finagling. And we're like, well, we're not going to finagle anymore. We're going to use time scales to say, to use, or to be able to model, because time scales allow for the simultaneous assessment of continuous time and discrete time. So as I said before, the field was introduced in 1988 by Stefan Hilger, and the goal was to unify and extend differential equations and difference equations. So I've said time scale. What exactly is a time scale? It's not a hard thing. A time scale is a non-empty, arbitrary closed subset of the real numbers. So most things you deal with are indeed time scales. So on the left, you have some examples. On the right, you have some non-examples. For the third example, we need to union 0. So we need to include 0 in that set to ensure that the set is closed. On the right-hand side, there's obvious reasons why those are non-examples. So most things you deal with are time scales, and R and Z are the foundational ones. We have theory of differential equations. We have the theory of difference equations. So when you move to a time scale, you always do this checking. If whatever I propose works on the integers and the real numbers, then I feel good about it. If it fails on any one of those, then I can't move forward, because differential equations has been around for forever, right? We've done calculus. You can't compete with calculus. If your work doesn't match on calculus, then there's some errors. So this is a time scale. So our time scale of choice is the union of these closed disjoint intervals. So why union of closed disjoint intervals? Because we want to be able to model you're on treatment, you're off treatment, you're on treatment, off treatment. And this time scale allows us to do this. So these closed intervals represent off treatment intervals. And you say, well, why are you modeling off treatment intervals instead of on treatment intervals? Well, we're modeling off treatment intervals because we know when a patient is not on, or a patient is off treatment, the tumor will grow exponentially, right? So there's a lot of data that talks about what happens when the patient is off treatment. So our time scale is made up of off treatment intervals. So the white spaces, the spaces in between, are the on treatment intervals. But this is our time scale of choice. So once you have any type of time scale, you have to know about sigma and mu. So I'm not going to go into the long definitions of this, but sigma is just your next neighbor. So who's to the right of you? So in the real numbers, sigma is myself because it's integers. I mean, sorry, because the real numbers are dense. On the integers, the next neighbor would be t plus one because there's two, then there's three, there's four, there's five. And then mu is the space between the points. So how far I am from my right neighbor. If you know what sigma is and if you know what mu is, you can talk about the time scale in any way. We use those things to describe a time scale. So for our time scale of choice, the picture is still on the bottom. If you are an endpoint, if you are right endpoint, then your space is just t, your sigma is t plus b, because you're going to jump to the start of the next interval. Everybody follow? Yeah, I can see y'all's faces, so give me some nods and not, okay. And then the space in between the intervals is b. So I know how to describe all the points in my time scale. Either we're really, really close together, or I have to jump to get to the next interval. With that information in mind, I can now work on building the dynamic equation. So on time scales, we call them dynamic equations. But in order to do that, we have to, before we build it, we're going to make some assumptions. So N of T is the PSA level, so the amount of prostate specific antigen that's in the, I want to say the tumor, goodness, the tumor at the time. We're going to assume that it grows exponentially because that's what the literature tells us. And we're going to assume that the PSA level depreciates at a constant rate. So this is our first time modeling this. So we make some very basic assumptions. Keep them simple, start simple, and then you can increase the complexity as you move along. The third assumption is the key one. That's key because it leads to the equation that allows us to build the dynamic equation. So what that says is at the start of one off treatment interval, right? Because it's depreciating as you move along. So we want to say that the volume is going to go down. Why is it going down? I was off treatment, then I was on treatment. So in the on treatment interval, of course, the tumor is going to shrink. So when I go off treatment again, I expect the tumor to have smaller volume. So we just assume that it's going to decrease at a constant rate of beta. Everybody follow? It makes sense. After you've been on treatment, you'd expect that the tumor volume to go down. So mathematically, that's represented by that equation of N of the quantity K plus 1 times the quantity A plus B equals beta, etc. That's what that means. That is important because it's going to allow us to build our dynamic equation. So if you want to build a dynamic equation, you got to have a derivative. This is the definition of the derivative on time scales. Notice that this is a piecewise definition because it matters what type of point you are. Am I a point where sigma of t is bigger than me, so there's some space between me and my neighbor? Or am I a type of point that sigma of t is equal to t? So sigma of t being bigger than t is what happens on the integers. Sigma of t equal to t is what happens on the real numbers, right? So fundamentally, this is the definition of the derivative. So that delta is what we use for the derivative. So this is the delta derivative. Now that I know what the derivative is, I'm going to look at my points, look at my points in the time scale to build my dynamic equation. So you got to start with an example. You can't generalize before you have some concrete examples. So we use the time scale P3, 5, and that turns out to be the union of the closed intervals 8K, 8K plus 3. So you have the graph here for some of those intervals. Everybody follow, 0 to 3, skip a space of 5, 8 to 11, keep going. So when I'm in the closed or the half open interval, so not exactly the endpoint, all the points are dense. This is basically being on a real line. So I can use the real derivative in place of the delta derivative, right? So n prime of t is going to be equal to ln of gamma n of t. Well, that's exponential growth. Here, it's key that we do not assume that the base is E. We're just going to assume that the base is gamma, where gamma is bigger than 1. I should have written that there. But the base is gamma, gamma bigger than 1. When we did this work initially, because these are the results I'm presenting, not all the work that we went through. Initially, we assumed that the base was E, and that was the wrong thing to do. And as we figured it out more, we assumed that the base just needed to be gamma. So then I replaced the derivative, the real derivative, with a delta derivative, because remember, I want to do this in general on time scales. So I have one part of it. I'm excited. Let's keep moving. Now what happens in the spacing? So what happens in the white space? What happens between 3 and 8? What happens between 11 and 16? That's when the patient is on treatment. So I'm going to expect that the tumor volume is going to decrease when I start the next off treatment interval. So 8K plus 8 and 8K plus 3 are off treatment points. But I want to talk about what happens in between them. And that is when the patient is on treatment. So the tumor volume should go down. So what I'm going to do now is build the derivative. So I've color coded it here. Hopefully you can see those colors to see that I'm going to subtract on both sides. You tell your students what you do on the left, you must also do on the right. Then I divide both sides by 5. Well, where does 5 come from? 5 is indeed mu. 5 is the space in between those intervals. And then what do I notice? That I've indeed constructed the derivative. So in purple, you should see that this is the derivative. I'm excited. I'm ready to go. When I did this before, we didn't realize that mu of t was the 5, honestly. We were like, I just know I need to build a derivative. I need to build a derivative. But we were getting lost in the numbers and not actually the representation of the numbers. And then once we realized that mu of t, that we were actually dividing by mu of t, it was good to go. So this is the dynamic equation when you are on the off treatment intervals. Yes, it's piecewise, but so what? It's okay. I have a dynamic equation. So next, what do you want to say? How do you solve this dynamic equation? That's what happens in your differential equation class. I give you a differential equation. Now I want you to solve it. So how am I going to solve this? Well, in DEs, we would use, one of the first things that we learned was separation of variables, right? Everybody remember separation of variables. There's no separation of variables in time scales, but there is an exponential function. Now, the exponential function doesn't look like the exponential function we're used to. It's called a generalized exponential function. And that exponential function is built from the cylinder transform. So why is this necessary? It's necessary because all the points are not dense points. When I'm on the real numbers, this generalized exponential is our natural exponential, what we expect. When I'm on the integers, the exponential is actually 2 to the t. It looks different. So your time scale determines what your exponential function is. Your time scale determines everything. So you have this generalized exponential, and we know that this generalized exponential is a solution to initial value problem. That was proven years ago. So we say, hey, can I make an IVP? Yes, I can. So we create an initial value problem so that we can solve it. So we look at this initial value problem, and we just say at the start of the time, you have some PSA level, and you had to, index it to make sure that all your indexes look great. So this is the dynamic equation, and we're still working on P35. Now, I'm not showing you the work here, but when you solve it using the generalized exponential, you get this solution. So you have E sub ln of gamma. And remember that E, we're talking about the generalized exponential. Then you also have E sub the quantity beta minus 1 divided by 5. But that's our mu. We're excited. We see how the pieces work. So I have a solution for my dynamic equation. Then it can be simplified to look like this. So once I use the generalized exponential, then it simplifies to look like this. So you see gamma, that's the base. You also see beta, that's the base. So now we have this solution. I can say at any particular time, this is the patient's PSA level. So why is this exciting? Because you can do some predicting with this, right? If they tell us, they being the cancer treatment center, if they say, I want this, or doctor, I want to think about my patient following this particular plan of treatment. Can you give me some idea of what their PSA levels are going to be at this time? We can, if the patient is on treatment and off treatment for a constant amount of time. So we were able to do that. So in general, this is what it looks like for a general time scale PAB. So A is the months off treatment and B is the months on treatment. And it turns out to be this nice solution. So we can make these predictions. We used MATLAB and FMinCon to simplify things, but this is what we get. So then you ask yourself, so you got it. Now, how does it compare to the data? Well, this is some of the results that we have. So there, Brukowski and his collaborators had 1,000 patients that did 100 patients that participated in the trial. And they used that information to model their, and to predict their PSA levels. And they did all of that with a differential equation. So we used that same data to see how our model stacked up. Well, because of our time scale, we assumed constant, that they were on treatment and off treatment for a constant amount of time. Of that data, there were only, let's say, 6 patients that really fell in line. So I'll talk to you about 3 or 4 of them today. So this is patient 77, patient 63. We just went through them and numbered them. So you'll see how we compare. We have some overshooting and we have some undershooting. Oh, then we're like, oh my gosh, this is not perfect. Okay, but it's our first go at it, so we're not going to worry about it. It's not perfect. We have some overshooting and some undershooting, but the fit is okay. I'm pleased. This is my first attempt to try to model. Somebody tell me what's wrong. So I go talk to my collaborators. I'm happy. They're like, this is good for your first try, Raegan. You can make it better. Okay, so we'll make it better. So again, you see overshooting, undershooting. In patient 60, you see this outlier way up there. We're like, who are you? Where did you come from? Why didn't our model catch you? So we know some things that we need to do to improve upon, but generally, we are pretty happy. We, me, my graduate student, that's the we. So now what are our next steps? What are we going to do to make this better? We know that we made a very simple assumption that it was constant treatment on, constant treatment off. That's not realistic. But in order to get started, that's what we had to assume just to see what happened. So now we've made some modifications to our original time scale. So we call them P tildes, AK, BK, AK, BK. So the AK says the A's, the months on are going to vary. BK say the months off are going to vary. And then AK, BK, everything is going to vary. So we expect that PAK, BK is going to be the one that's going to work all the time. That's what we're hoping for, because that's more realistic. So visually, you can just see, just another way to think about it. We're going to compare these time scales. So we want to see which one of these works better. So we're in the process now of figuring out which one works better. And from what we've seen so far, PAKB is not the best one all the time. And we have to figure out why that is the case. So we thought we were there, it's not there. So, but we're close. So now we're gonna figure out what glitches are happening with PAKB not being the best one all the time. So is it that we're not feeding the data the right way? Do we need to go back and check our code? And people that code, you check it multiple times and you're like, okay, fix this, but if I change this, what does this impact on this side? So right now we're at the stage of figuring out what's the best model. And then once we have the better time scale, we're going to redo the dynamic equation to see if that's going to work. And we want to introduce what's called fractional calculus. So fractional calculus is when your power of your derivative is not a whole number, right? It can be a fraction. And we've seen some success with modeling tumors in mice using fractional calculus. So those are our next steps to get the best model that we will be able to optimize, right? Because the goal is to say, based on my patient, what is the treatment plan that I should put him or her on? How long, or him, since it's prostate cancer, how long should he be on treatment? How long should she be off treatment? And then can we take this and generalize it to other types of things? So that's what we're working toward. So hopefully you understand globally one of my research topics. Now I'm going to talk about broadening mathematics. What does that mean to me? So as you heard before, women in STEM was something that wasn't a big deal in my life. But as I progressed in the field, I learned that being a woman in STEM was a big deal. So I've made it formally, informally, my service mission to support communities that are historically excluded from STEM. So whatever those communities are, I want to find ways to support you. So what things have I done? My epiphany actually came as a result of attending Nebraska Conference Undergraduate Women Mathematics in February of 2001. I don't recall there being another Black person at that conference besides myself. So coming from a HBCU where there are tons of women, tons of Black women doing math, we were the majority in the class. I go to this conference and I present and I'm like, where's me? What is happening here? Has somebody lying to me? Are they telling me, encouraging me to go in this field and there's no representation? Do I really want to be in this field? So at that moment being the end of my junior year, I did question if this is something that I really want to do, but I was successful, whatever successful means as, being an undergraduate student, and, keep going. It'll be fine. I don't know about this. It'll be fine, but I'm going to trust the people that have gone before me to say that it's going to be fine. So I did indeed go to graduate school, but after that experience at the Nebraska Conference of Undergraduate Women, I was just like, I don't know that I want to do this. So when I was at UNL, I participated. So I was a graduate student member of the organizing committee because we got to increase the representation. This cannot happen to anybody else, at least while I'm here, that she is the only brown person that she sees in this room, because it's also about building community, right? How am I going to build community that does not necessarily represent me? I want to be able to contribute to the community and also receive from the community. So that was important to me. So I was a graduate student panelist. I became an invited graduate student. I was on the organizing committee, and then eventually I was an invited guest. So the top picture, that's myself sitting there. If you see, this is my advanced calculus notebook. So I'm studying baby reals while I'm there because that's the class that I was taking. And underneath me is Tahira Darensberg. She went to Xavier as I did. Her advisor was also Dr. Kosick, and she came to the conference to present. So I was very, basically like Dr. Kosick told me that I'm gonna go, I told her, now you're gonna go. So it was good to start bringing people into that community. When I got to Texas Tech, I helped found the Young Women in Mathematics. So I was the assistant professor. There was assistant professor, associate professor, and a full professor. And we said, we need to help the young women in our department find their place and be comfortable in this field. So we found a Young Women in Mathematics. This is one of our very first meetings. And what we did was have a Women of Excellence lecture series. So we started bringing women outside of our universities to come and share your experiences. So Dr. Tanya Moore is one of the first people that we brought to share, to say, this is how I got on this journey. This is what I do. These are the things that you can do. I can help you out to broaden your community. So that was something that was and still is important to me. And I didn't let that stop once I got to graduate school. Once I was done, it's like, okay, I've quote made it, right? I'm now on the tenure track. So now you have to bring other people along. So that's something that I do. I also a part of the EDGE program. So I participated in EDGE in 2002. So as I was graduating, that top picture on the left, that's me with that denim dress on. And EDGE was my saving grace during graduate school. It was the place that I knew that I could go and I could be who I was and not worry about being smart enough or do I understand this? I could just say, I don't understand. Somebody help me. I do understand, but I want to be better. So it wasn't a community that ended once I had graduated, right? Now you're in graduate school, you keep going. So I began teaching for EDGE in 2014. and I taught 4 years, 3 years, and then I became a co-director in 2017, 2018. Edge came to Texas Tech, and that was important to me to bring Edge to Texas Tech so that my colleagues could see the things that I'm passionate about. It's not just the young women at Texas Tech. This is a global interest of mine. So Edge was at Texas Tech in 2018. Then we had our first virtual Edge last year because of COVID. So that's the painted picture in the middle with the women with no faces, because we had to take pictures together and make it all come together. So it's been an experience. We haven't let COVID defray us or stop us, derail us from building this community. So Edge is one thing that I continue to do. And then my latest endeavor was Mathematically Gifted and Black. So I met Candace, Erica, and Shelby as a result of Edge. I was a part of the Siam workshop for celebrating diversity in some time. I was for 3 years. And I reached out to my Edge community and I said, who do I need to invite that is on the track to get on stage? And they suggested Shelby and Erica. And that was the first time that I met them. And I knew they were doing math bio. And then I met Candace. And in 2016, Candace said, we should do this. This is largely inspired by Latism. She said we should do it. And we were like, okay, we're gonna create a website. So jokingly, we call ourselves 4 Homegirls in a Website, because that's how it started. It was just our interest to show Black mathematicians. And we said, this is what we're gonna do. So we put our resources together, we got a website, and we reached out to our friends and we said, this is what we're gonna do, support us. And then they said, okay. And then we built a website, and then we kept going and we kept going. And this year is year number 5. So we are excited to continue to do this. And it's a part of our mission to support, or my mission, I'm sure theirs too, to support the community, right? To make sure that there is representation and that young people, little people, college students, graduate students still see themselves in a field that they are passionate about. We don't want them to feel like there's no space for them. There's no place for them. You can be in this field. So this is a quick bibliography. Number 1 is the data. Number 2 is the paper we published. Number 3 is the book that we call the Green Bible. So it talks about all dynamic equations on timescales. So if you want to learn anything about timescales or the work that we're doing, this is what you can refer to. Thank you very much.
Thank you.